This week in lab, we will be dealing with acids and bases and acid-base reactions. We'll need to know a little bit of stoichiometry, but we're going to start with our basic definitions of acids and bases. The simplest definitions are the Arrhenius definitions of acids and bases. So Arrhenius said that an acid will produce H+ when dissolved in water. So a hydrogen ion will be produced from the molecule when you put it into water. So here's hydrogen chloride or hydrochloric acid. When you dissolve that into water, it will produce a hydrogen ion and a chloride ion. The Arrhenius definition for a base is that it will produce hydroxide ion when dissolved in water. So OH- is the hydroxide ion. It's a polyatomic anion. When you dissolve sodium hydroxide into water, then sodium gives up its only valence electron to the hydroxide anion. When you have a neutral solution, you have a pH of 7. And so over here we have just a pH scale to give you an idea of the common liquids that are acids and bases. pH of 7 is a neutral. What that really means is you have equal concentrations of hydroxide and hydronium or hydrogen ion in solution. Distilled water, for example, has a pH of 7. Basic solutions have pH that are greater than 7, and acidic solutions have a pH that are less than 7. So stomach acid is here between 1 and 2, lemon juice, black coffee, etc. Baking soda, soapy water, soap and bleach are up here at the top of the list in the basic range. When we do an acid-base reaction, it's called a neutralization reaction. So we have hydrochloric acid reacting with sodium hydroxide base. And what happens is the cation switches places with the cation on the other molecule. So this is called a metathesis reaction, where we have our hydrogen ion is going to react with the hydroxide ion from the base and create water, liquid water. What's left over is the sodium from the base and the chloride from the acid, and that comes together to make a salt. So we get water and a salt. The main products of any acid-base neutralization reaction will be water and salt. I just told you that an acid will, according to the Arrhenius definition, produce hydrogen ions as well as chloride ions in water, and the base will produce hydroxide as well as sodium. We can write out all of those ions explicitly instead of calling them molecules here. So we would have a hydrogen ion, a chloride ion, sodium ion, hydroxide ion, and the hydroxide and the hydrogen are going to come together to make liquid water, and we have leftover sodium and chloride. The sodium and the chloride we would call spectator ions. They're the same on both sides of the chemical reaction, and so we can kind of get rid of those to look at the reaction that's actually occurring, which is a hydrogen ion plus a hydronium ion is making liquid water. So the products of any neutralization reaction are an acid plus a base, make water and a salt. Okay, the salt is coming from the spectator ions, which in this case is sodium and chloride, and the actual reaction that we would care about is going to be hydrogen ion plus hydroxide ion makes water. Now, how do we do calculations with this? Or what calculations would you be expected to do with this? Any calculations, these are stoichiometry calculations, but any stoichiometry calculation comes down to unit conversions. That's all this is, and don't make it more complicated than that. The conversion factor that we use to answer these questions comes from the balanced chemical reaction. So here is the balanced chemical reaction for acid plus base, right? Makes water plus salt. And if we want to know how many moles of sodium hydroxide would be required to completely neutralize 0.37 moles of hydrochloric acid, well, we're going to start with the numbers that they've given us, 0.37 moles of hydrochloric acid. we're going to convert that into an amount of sodium hydroxide by using the balanced chemical equation. Now, what about the balanced chemical equation? We're going to use the coefficients for each one of these species. So I want to convert between hydrochloric acid and sodium hydroxide. Hydrochloric acid has a coefficient of 1. Okay, sodium hydroxide has a coefficient of 1. You may notice that 1s are not usually explicit in balanced chemical equations, but they are there. And so what we can write is for every 1 molecule of HCl, we get 1 molecule of NaOH in this reaction, or 1 mole of HCl to 1 mole of NaOH. So if I'm trying to convert between HCl and NaOH, I'm going to use a conversion factor that allows me to cancel out my moles of HCl and give me moles of NaOH. So I've got 1 mole of NaOH, and that's because there's a 1 in front of NaOH in the balanced chemical equation. And I've got 1 mole of HCl because there's 1 mole in the balanced chemical equation. And so I've got 0.37 moles of NaOH. That's pretty straightforward. I hope you think it is straightforward. A better question, something that looks more like what you might need to do, is how many milliliters of 0.5 molar NaOH solution are required to completely neutralize 25 milliliters of 0.2 molar HCl. Now, don't let this freak you out. You still need to come back to that mole to mole conversion. But what that means is you have to convert what you know into moles first, and then use a conversion factor based on the balanced chemical equation, and then come back out of moles to whatever your desired product is. So we know enough information for HCl. We know a volume and a molarity to get to moles. Okay, so we're going to do that first. So I'm going to take my molarity times my volume. Liters are going to cancel out, and I'm going to get moles of HCl. Now I can use my balanced chemical equation to do a conversion from HCl to NaOH, and then I'm going to use that moles of NaOH that I've just found, as well as the concentration of NaOH that I was given, to determine the volume. Okay, so moles divided by moles per liter basically is going to give me liters. Okay, and so 10 milliliters of NaOH would be required to completely neutralize the amount of HCl that I'm given. The strategy for any stoichiometry problem or any acid-base reaction problem can boil down to this mole island diagram. Okay, if you're given a mass, perhaps, of an analyte or a compound, you can get to moles via the molar mass. If you're given a number of particles, you can use Avogadro's number to get to moles. In this case, we will be using molarity and the volume to get to moles. Once you have moles of the first thing, maybe that's your acid or maybe that's your base, then you can use that mole ratio from the chemical equation to get to moles of the other thing. And then you can get out again to any of those final units that you require. The key thing here is that this centerpiece, the moles of A to moles of B, where you use the mole ratio from the chemical equation, that is the heart of any stoichiometry problem. You cannot do a stoichiometry problem without going to moles and then using the chemical equation to do a conversion in moles. You cannot go directly from molarity to grams or from molarity to particles on the other side. You have to go to moles first and then convert between moles. So let's try another problem. Polyprotic acids have more than one proton that can be donated in an acid-base reaction. So here we have sulfuric acid, H2SO4, and both of these hydrogen ions can be removed from sulfuric acid to react with hydroxide and make water. Again, polyprotic acids are just like any other acids, acid-base reactions, where you have an acid plus a base is going to make water and salt. The only difference here is that the stoichiometry is different, which means the coefficients in this reaction are slightly different. We can write out all of the ions. Okay, if it's aqueous, it means that it's dissolving and separating in water. So I have 2 hydrogen ions here. I have 1 sulfate anion okay, which is a polyatomic anion. I have 2 sodium ions, I have 2 hydroxide polyatomic anions, and then I make 2 molecules of water. I still have 2 sodiums and 1 sulfate left over. So the sodiums and the sulfates get left over as spectator ions, and the thing that we actually care about is that 2 hydrogen ions will pair with 2 hydroxide ions to make 2 molecules of water. So we can do a calculation with this as well. How many moles of sodium hydroxide are required to completely neutralize 0.37 moles of H2SO4? Again, we'll start with what we're given, 0.37 moles of H2SO4, and then we're going to use the coefficients from the balanced chemical equation to solve this problem. So H2SO4 sulfuric acid has a coefficient of 1, and sodium hydroxide has a coefficient of 2. So I'm going to make a conversion factor here that's going to have sodium hydroxide in the numerator and sulfuric acid in the denominator. Now I can do my math, and I find I need twice as much sodium hydroxide as I do sulfuric acid, and that's because there are 2 protons here for every 1 sulfuric acid. Again, how might this actually look in practice? We might want to know how many milliliters of a 0.12 molarity solution are required to completely neutralize some amount of sulfuric acid. So here again, remember that mole island diagram, we need to convert to moles first and then use the balanced chemical equation to create a conversion factor between sulfuric acid and sodium hydroxide. So milliliters and molarity can work together to give us moles, right? Moles per liter times liters. It's going to give me moles. And then I'm going to use my conversion factor from the balanced chemical equation, sodium hydroxide in the numerator, sulfuric acid in the denominator, to cancel that out. And I'll get moles of sodium hydroxide that are required. And now what I want to find, right, is how many milliliters, or what is the volume, but I'm given the molarity. So my moles divided by my molarity basically is going to give me my volume. And so that turns out to be 83 milliliters. A final example here is phosphoric acid has 3 acidic protons. So this is another polyprotic acid, except now my stoichiometry between phosphoric acid and sodium hydroxide is 1:3. You pause the video here and try this problem on your own. Okay, so this problem, again, we are starting with things that we know about sodium hydroxide, and so that's where we're going to start. We're going to go to moles of sodium hydroxide, and then we're going to use the balanced chemical equation to convert from sodium hydroxide into phosphoric, and then we're going to use the moles of phosphoric acid and the volume of phosphoric acid to determine the concentration of phosphoric acid. So we're starting with the molarity and the volume of sodium hydroxide. To find moles of sodium hydroxide, we'll use a mole ratio from the balanced chemical equation to find the moles of phosphoric, and then we're given the volume of phosphoric, and so we can determine the molarity of phosphoric acid. So molarity of sodium hydroxide times the volume equals the moles of sodium hydroxide. Use my balanced chemical equation. I'm going to put sodium hydroxide in the denominator so that I can cancel out my units and get moles of phosphoric acid. And then moles of phosphoric acid divided by liters of phosphoric acid will give me the concentration of phosphoric acid.